So we have, if we have electric field, if we have an equation describing the electric field, we can integrate it and find potential difference between any 2 points. Potential difference, negative integral of E dot dr. Well, we should be able to work backwards. If we have an equation for potential difference, we should be able to work backwards and find our electric field as well. If we take off our integral and solve for E, we're going to find out that the electric field is the negative derivative of the potential with respect to position. Now, those are partial derivative signs. The potential can depend on your x direction, your y direction, your z direction. Electric field is a vector. To get the components, we need to take the partial derivative with respect to those specific variables. For example, to find the electric field, the x component of your electric field, you need to take the derivative of your potential with x being your variable. That means you treat any y's and z's as if they are constants. If you want the y component of the electric field, you need to take the derivative with respect to y being your variable. And likewise with respect to z being your variable. If you've not done partial derivatives before, they're really quite easy. At least the ones we're going to do. Let's say we have a potential. I'm in no way claiming it to be representative of any actual real physical situation. I'm just making up an equation. So our potential, the value of our potential at any point depends upon where you are on the x-axis, where you are on the y-axis, and where you are on the z-axis. So it depends upon your x-coordinate, your y-coordinate, and your z-coordinate. Now, potential itself is a scalar. It just has a value. It can be positive or negative. It's just meaning it's high or low. But it doesn't have a direction associated with it. So to get our electric field at any point, the x component of electric field, don't forget the negative sign. That's the easiest thing to forget. It's just part of the equation. So negative sign, we need to take the derivative of our potential function, treating only x as the variable. So the y's are going to be treated as constants, and the z's are going to be treated as constants. So the derivative of this first term, the 2 and the y are treated as constants. The derivative of x squared is 2x. So the derivative of that term is 4xy. Minus the derivative of this second term, well, the y is a constant, z is considered a constant. So this whole term is a constant. Derivative of a constant, 0. So the x component of our electric field is negative 4xy. So it still depends upon where you are in the coordinate system.
I missed where that negative came from. Is that because it's built in?
The negative sign's in the equation itself. So the y component, what will the first term be? You treat y as your variable, you treat x's and z's as constants. Right, 2x squared is a constant, derivative of y is just 1. So here the 3z are constant, derivative of y is 1. So the y component of our electric field is negative 2x squared plus 3z. The z component of our electric field, now we treat z's as variables and x and y's as constants. So the first term does not have a z in it, so that will go to 0. The second term, the 3 and the y are constants, derivative of z is 1. So our z component of the electric field is simply 3y. So we could say our electric field vector is equal to minus 4xy I hat plus the quantity of negative 2x squared plus 3z j hat plus the quantity of 3y k hat. The electric field depends upon the position, where you are in the coordinate system. So let's say we wanted to find the electric field at the point 1, 1, 1. Make it easier on ourselves. If you want, we could change that up a little bit. So that means in a coordinate system, 1 meter in the x, 1 meter in the y, 1 meter in the z. So a point out here. The electric field, plugging in 1 for x and y, our electric field at that point has a value of 4, negative in the negative x direction. So putting in 1 for x and y here, we're going to get negative 1. That's the j hat direction. Sorry, positive 1. Plus 3 j hat. Now units. This term had units of volts. When we were taking the derivative with respect to position, that gives us volts per meter. Volts per meter is a perfectly valid unit for an electric field. A volt per meter is the same thing as a Newton per coulomb. Which, if you remember, we said a volt was a joule per coulomb, and a joule is a Newton meter per coulomb. Bring your meter up, your volt's a Newton meter per coulomb. So that means volts per meter is equal to newtons per coulomb. It's easy to find the magnitude of the electric field as well. If you wanted to know this is vector notation of the electric field. It gives us the x, the y, and the z components. Right. You just want the magnitude. It's just Pythagorean theorem. Pythagorean theorem works fine three-dimensionally. So it'll be what, 5?
5.1.
Oh, sorry, I forgot the 1. I was just looking at these guys and was excited they added to 25. As far as the partial derivatives are concerned, we won't do anything more complicated than some sort of polynomial type equation. So
That'll be given to us?
you would be given the equation for potential and asked for electric field, for example.